So hi everyone, I'm Joe from Poolside, and I just want to give you some context about Poolside and what it is that we do. So Poolside is a frontier AI company that is pursuing AGI by building AI models for software development. Now that's a very ambitious goal, and from our side that demands obsession. And in particular, that obsession stretches through everything we do, including the performance of our inference stack. Now at the moment, our inference stack is primarily based on PyTorch, admittedly mixed in with some Triton and some CUDA to give high performance. The reason why I'm telling you this is because I view us as the typical non-trivial case. We're the case where you have existing code that needs to be ported, there's some things that you need to change, and I just want to talk to you about our experience with that. In particular though, there's two added things that have made porting for us perhaps slightly more difficult than in your case. So firstly, we are performance obsessed. I'm like a lawyer, I will debate every cycle. And for us, this means that we can't accept any slowdown at all in the speed of our inference. The second thing is that we regularly try out new ideas in our inference stack. And so for us, if we had to re-implement everything multiple times, that would be a non-starter. I do want to stress though, that even though I've just listed the barriers in the way, it hasn't been a problem in practice when it's actually come to porting things to Neuron. And I want to give you some high-level tips and tricks that we've learned along the way to help you if you decide to make the transition. So, sorry, I should have done that earlier. So the first tip that I want to share with you is that you need to change your mindset. So when we came to port our platform onto Neuron, we essentially took the PyTorch code that we had, copied it over, put it onto Neuron, and then we worked around the Triton and CUDA that we had. Now this mostly worked straight away, which we were quite surprised at, but of course there were some things that we needed to change and fix. And fundamentally for us, that tended to come down to where we were still operating under a different mindset. So we were still thinking about writing code, say for CUDA. And it's not really quite the same when it comes to writing things for Neuron. I would liken this to learning a new language that is similar to one that you already know, right? You know, for the first little while, you're trying to build understanding, you're stumbling around, but eventually you get to a point where you understand how the system works. And for us, I'd say that that took roughly about a week. It really didn't take us that much time at all once we sat down and got into thinking about it. But of course, as with any language, we learn every day and the process continues. But I do want to point out that it's worth changing your mindset from what you think is fast to what is actually fast when it comes to Neuron. Now, the second tip that I want to give you is to use the tools that you're given. So Gadi just spoke about the Neuron SDK. In this case in particular, I'm talking about using the libraries that are provided in the Neuron SDK. So NeuronX Distributed and Torch NeuronX. When we came to port our code, as I already mentioned, we just took our PyTorch and copied it straight over. And after we fixed some things, it worked. But we weren't necessarily getting the performance that we wanted. And completely coincidentally, we switched to use the tracing that's offered by one of those libraries that I mentioned, and we got a 100% speed up across multiple devices. Now, this wasn't something we expected. We were trying to solve something completely different, but it was obviously a performance thing that we took. And I want to point out that by taking advantage of the platform in whatever way you can, you do tend to get more out of the Neuron hardware. In the language analogy from before, this is like using idioms and catchphrases that you've learned from your new language, right? You aren't just doing direct translation, you're picking up things that will help you contextually. Now, this in particular, exploiting the hardware, is about writing code that is actually dedicated for Neuron. So when we started, like I said, we ported over with PyTorch. The PyTorch tracing compiler is superb, by the way. It works most of the time. We rarely run into hard limits that we can't beat. But as a developer, you know that there are situations where you can out-optimize the compiler because you can make assumptions and decisions that it simply cannot. And for us, in this case, we used the Nikki language, which Gadi just mentioned. The important thing there is that you can write things in a Pythonic flavor that takes direct advantage of the underlying hardware. You can specify operations that explicitly use certain engines or use certain hardware features, and you can profile it perfectly with the Neuron profiler. One of the really nice things about Nikki, as I said, is that it's Python-esque, essentially. So you are able to pick it up very quickly if you know Triton or any other Pythonic language. You also don't need any low-level assembly experience. You don't need any deep technical knowledge of like linking or anything like that. You can simply write something that's very familiar and very concise, and it's very, very easy to pick up. One of the nice things about Nikki in particular, and also the Neuron hardware, is that it enables you to express very succinctly ideas that you can't otherwise. So for example, in our case, we've written some specialized kernels for doing the token generation in the inference step. And these are very succinct kernels, they're maybe 50 lines or so, but you can get something like a 100 times speed up in the inference step and a 2 times speed up in the prefill step, so when you're processing the prompt at the beginning. And this is money that's lying on the ground, right? You have to pick it up. I just want to stress that last point again. So something that we've noticed as we've been using this platform is that a great deal many kernels that you'll see are based on this top case here, right? They're considering matrix operations, which is great. You can process your prompt very, very quickly. But actually, we found that this is not always what you're spending your time doing when you're doing inference. You're actually spending more of your time doing the second type of operation, where you're taking a vector and you're multiplying it by a matrix, or you're adding to a matrix, or so on. I won't go into the technicalities or the details of how we've done this, but we've spent a great deal of time optimizing our kernels for this second case. And just to give you an idea, we're now in the unique position where the attention mechanism in our inference is no longer a bottleneck, which is quite unusual. And this is simply because we've spent so much time tweaking our kernels and adapting them directly to the Neuron hardware with Nikki. But of course, we always like more hardware. And as someone who's been working rather closely with the Annapurna team, we've been able to get early access to Trainium2. Now, I'll be honest with you, switching to Trainium2 was quite frankly, a magical experience for us. So we just took the code that we had, we put it on a Trainium2 box, and we got 50% more performance for free. I didn't change anything. And that's quite, an unusual experience. But there are other nice things about Trainium2 as well. So firstly, Trainium2 has 128 neuron cores in each instance, which is 4 times as many as in a Trainium1 instance. So right off the bat, you can serve 4 times as many copies of your model per instance, which for us was a big win. The second thing that I really like about Trainium2 is Trainium2 has support for this thing called virtual cores. So I just said that Trainium2 has 128 physical neuron cores, but you can group 2 of those at a time into one virtual core from the perspective of your software. And this gives you a couple of advantages. So firstly, it means that you can present more memory to your application. In this case in particular, when you use the virtual core grouping, you get 24 gigabytes of HBM per virtual core, which is more than the 16 gigabytes of HBM per neuron core that's offered in Trainium1. The second thing, of course, is that you get even more on-device parallelism. Right? You have 2 cores that are processing the same amount of work, which is an amazing use case, right? As AI applications get larger and there tends to be more and more stuff that's going on, having the ability to churn through all of that input faster is a complete game changer. And even when you do that, even when you group those 2 cores as one virtual core, you still have twice as many instances per box. So you still have 64 virtual cores per box, which is twice as many as on Trainium1. And for us, this is an unbelievably useful feature and it's something that we look forward to taking advantage of. Now, I just want to show you some performance numbers. I want to stress that these numbers are entirely provisional. We've still got a lot of work left to do in terms of optimization. On the left here, you can see our numbers for Trainium1. So you can see that at a 2K context length, we get about 26 tokens a second, and that drops down when you come to the 4K length. In the middle there, you have Trainium2. Now this is just naively ported. We haven't done any optimizations at all for Trainium2 on that middle set. And you can see that you get that free roughly 50% increase in the 2K length, slightly less in the 4K context length, that's okay. And this last column at the end is the elephant in the room. Now, I've just spent all of this time talking to you about how you can optimize by using 2 cores as one virtual core. But actually, when we profiled our model, we discovered that we weren't actually using both cores fully in every situation that we could. Now, thankfully, Nikki has this nice new feature coming called sharding, which enables you to explicitly say, hey, I've got this input data in this Nikki kernel. I want this core to process this, and I want this core to process this. And of course, this just lets you explicitly specify what parallelism you want and how your data should be processed. And as you can see, this leads to a substantial performance increase even over the regular Trainium2 code. Admittedly, it drops down a little bit for the 4K context length, but as I said, this is primarily because we haven't truly finished optimizing yet, and we look forward to continue to optimize this code for Trainium2.